One way we can analyze how a satellite orbits the Earth is to look into what we call the energetics of the orbit, the exchange of kinetic and potential energy over time, and how the sum of these, the total energy, remains constant. Let's start by pausing the simulation so we don't have to worry about getting distracted by the satellite flying around. One thing you might find confusing at first is that on both the left and right-hand graphs, the potential energy is listed as a negative value. And since it is more negative than the kinetic energy, the total energy is also listed as a negative value. This is confusing because we often think of objects starting on the ground, on Earth, with zero potential energy stored, and then increasing in potential energy as we lift them, so always a positive value. Remember that we can set the zero level wherever we want. We can, for instance, set it at the surface of the Earth, but we could also set it at a tabletop or at a sea level or anywhere. The decision we make about that is arbitrary. We can choose any level we want to be the zero level of potential energy. What would make sense when looking at the solar system from outside? One consideration we often make is as follows. Imagine the satellite is far away from everything, in deep space, just sitting there. Well, let's call that zero potential energy. Then, as the satellite approaches Earth, it should still lose potential energy, and so it has to go negative. One nice thing about this way of thinking about energy is that the sign of the total energy, positive or negative, tells us something about the orbit. When the total energy is negative, the orbit is said to be bound, meaning the satellite doesn't have enough energy to make it to free space and just drift along forever. So it is stuck, if you will, in orbit. When the total energy is positive, on the other hand, the orbit is unbound and the satellite can escape. Let's increase the initial speed of the satellite so that it has enough energy to escape and see what happens. You'll notice a very special thing happen when the kinetic energy is exactly half the amount of the potential energy, and the sign is changed too. The orbit is circular. It is a common property of circular orbits that the kinetic energy is half as much as the potential, with a sign change. This is a fun theorem to prove with an advanced treatment. When you are playing around with this simulation, keep an eye on the vertical axes of the two graphs. They are plots of energy, but you'll see that there is a coefficient of a 10 to the 12th power. This means the energies are measured in trillions of joules. Huge. I also think you should look at what happens when you start an orbit with too little energy to achieve circular orbit and too much energy to achieve circular orbit. In both cases, you end up with elliptical orbits with the Earth at one focus of the ellipse, but they differ in the orientation of the ellipse. Thank you for watching.